Today we will be discussing about a new method, and that is iteration method. So in this method also we will be learning how to find a root of a given function f of x, but using a different method. So in the last two methods, that is the bisection method and the regular falsy method, we studied that how to determine a root or a root of a function with the help of a interval. So here in iteration method we are going to use another form, and we will look into the steps that we have to follow when to find a root of a function when it is given. So now let's have a look at the steps that you have to follow when you do the iteration method. So these steps you just keep in your mind. These steps will be more clear when you do a problem. Okay, so as usual, when a function is given to you, so for example, if your function is f of x is equal to 0, then sometimes you will be provided with the two intervals a, b. Okay, if in case if a and b is not provided to you, you will have to find. So the first step is you will have to find a comma b such that f of a and f of b are of opposite signs. Okay, so the first step is nothing but you will have to find a and b such that f of a and f of b are of opposite sides. I hope you have done these kind of steps in the bisection and regular falsy method. Now, this step can be omitted if your problem does not have, if your problem, if they have given you a and b, then you can of course avoid this step. Okay, now after finding f of a and f of b, you will have to find the initial root, and I am denoting the initial root by x naught. So in iteration method, the initial root can lie between anywhere between a and b, and you can give your initial root anything. Like if a is like 0 and b is 1, then you can give your initial root as 0.5, or it could be given as 0.48 or 0.6. So it's all up to you. Okay, so that's it. You have to find out the initial root, that is x naught. After finding the initial root, the third step is the most crucial step. That is, if you are given a function f of x is equal to 0. Now I haven't written any example over here. So when I move on to the example, you will understand this step more clearly, the third step. So you will have to express your x in terms of another function called phi of x. Okay, in this way you will have to represent. So this again I am repeating this, you will understand it more better when we move on to an example. So just keep this third step in your mind, that is express x in terms of another function called phi of x. Now the fourth point is that now as soon as you find out phi of x, you have to find out what is phi dash of x. That is, you have to differentiate this phi of x. Okay, so differentiate the phi of x, you will get phi dash of x, and then your phi dash of x should be less than 1. That is, modulus of phi dash of x should be less than 1. I am only just taking the quantity. I am not considering it whether a positive or a negative quantity. The only thing, that's why I have given the modulus sign, or the absolute value of phi dash of x should be less than 1. That is only my condition in the iteration method. Now the fifth step is that I'm going to give you an iteration formula. Now the formula is xn plus 1 is equal to phi of xn. This is my formula for iteration. Okay, this also you just keep in mind or note it somewhere else, so that it would be easier when you do the problem. Now, since this is my formula, now you will have a thought in your mind, like how many times should I iterate, or till when should I stop the iteration? Yes, so the sixth step is that can stop your iteration. You can stop your iteration when this condition is satisfied, that is xn the value of xn and the value of xn plus 1. When this condition is satisfied, you can stop the iteration at once, and then you can come to a conclusion that the real root of that particular function is so and so, that you will conclude it by yourself. But you can only conclude it or stop your iteration only at this point. Okay, when this is satisfied, this final condition is satisfied. So now we will solve the problem. So my function over here is x cube plus x square minus 1 is equal to 0. This is my f of x. Now here I am not provided with any a or b, or I am not provided with the interval. So I have to find out a and b such that f of a and f of b are of opposite sides. So by now I think you will be familiar about that. If you are not familiar, you can go and brush up how to find out a and b such that f of a and b are of opposite signs in the regular falsy or by the bisection method. So I'm going to, first step over here is I'm going to find out a and b, and I found out a and b because I just checked whether f of 0 is equal to a negative quantity or f of 1 is equal to a positive quantity. So that I got it as two different signs, and then I came to a conclusion that my a is equal to 0 and b is equal to 1. So for me it is actually somewhere the root lies between a and b, or 0 and 1. Now my next step is to give an initial value for x0, or the initial value for the root is right now I'm going to give it as 0.5. That 0.5 is again somewhere between 0 and 1. Okay, it lies exactly in the middle. So it's not somewhere, it's exactly in the middle. So I'm going to give as 0.5. If you are not happy with 0.5, you can give it as 0.4. That is all up to you. So right now I'm going to take the middle value, that's 0.5. I'm only just concerned about whether it lies between 0 and 1. That's only my concern. Okay. Now, according to the iteration method, now next step is to represent our x in terms of another function called phi of x. Now let's have a look at how to express our x in terms of another function. So as you can see, I have given here 3 columns. Now you will be wondering why these 3 columns. So I will explain that to you later. Now let's consider this first column. Okay, so and again our function. So our function here is x cube plus x square minus 1 is equal to 0. Now from this I have to express x is equal to some other function. Now if I take x cube here alone and take the other values to the other side, I will get 1 minus x square. Again x is equal to 1 minus x square the whole raised to 1 by 3. So see, so here x is expressed as another function. Okay, now what was the next step? Next step was to find out. So x is equal to phi of x. This is clearly in terms of x is equal to phi of x, right? Now you will have to find out what phi dash of x. Now here your phi of x is nothing but, what is it? 1 minus x square the whole raised to 1 by 3. Okay, now you have to find out phi dash of x. Now what is phi dash of x? Phi dash of x is nothing but, you have to do the derivation over here. When you do the derivation, you get 1 by 3 into 1 minus x square the whole raised to minus 2 by 3 multiplied by this thing, that is what, minus 2x. Okay, this is, I hope you all know how to do the derivation. So just these are all simple derivation. I don't want to go back to your high school level. So by derivating this, I will get the final answer. I'm going to just refine whatever I have written over here. That's minus 2 by 3 x in the numerator. The whole divided by the denominator part, I'm going to take it like this, 1 minus x square the whole raised to, since this is negative value, 2 by 3. So this is my phi dash of x. I'm going to write this as case 1. Okay, now you will be wondering why I have written like this. Okay, so just keep all these things in mind. This is case 1. See, when you have a close look at your function x cubed plus x square minus 1 is equal to 0, there are 2 more other ways of expressing your x. Okay, this is not the only way of expressing x in terms of another function. So there are two more other ways. Now we will have to check what are the other two ways to express x in terms of phi of x. So the first method, the first case was this, expressing like this, that is x is equal to 1 minus x square raised to 1 by 3. Starting from here, I just came down to here. I also found out the derivative, that is phi dash of x also of this case 1. Now let's move on to case 2. Okay. So case 2 is when, again I am going to take this, consider this function, and I am going to keep this x square here and take the other two things to the other side. So what are the other two things? X cube and minus 1. So when I take that to the other side, I get what? 1 minus x cube, right? So x is equal to 1 minus x cube the whole raised to minus 1 by 2. Okay, sorry, plus 1 by 2. Okay, this is what you get here. So see how different this case 1 and case 2 is. Right, so that is why there was a possibility of the three ways of expressing x. So here the phi dash is 1 minus x cube the whole raised to 1 by 2. Now again I am going to differentiate phi dash of x. When I differentiate differentiate phi of x. When I differentiate phi of x, I get phi dash of x, and phi dash of x is nothing but what is it? 1 by 2, 1 minus x cube the whole raised to minus 1 by 2 into 3x square, which is equal to, okay, which is equal to, what will I get now? 3 by 2 x square. Now here the denominator part is 1 minus x cube raised to 1 by 2. So this is the the second case. Okay, similarly we will have a third case too. So the third case is I'm going to consider, I'm going to take the first two terms into consideration, and I'm going to take x square outside, so that I get x square into x plus 1 minus 1 is equal to 0. Now I will get x square is equal to 1 by x plus 1, and x is equal to 1 by root x plus 1. So here my phi of x, again in case 3, my phi of x is 1 by root of x plus 1. Okay, now again I am going to find out phi dash of x. Phi dash of x is equal to 1 by 2 into x plus 1 the whole raised to 3 by 2. Now you will have a confusion, like there are three cases over here, and which phi dash of x should we consider. Okay, so that we will so the next step is to find out which is the most suitable phi dash of x among this among the three cases. So now this is a particular problem because it's our function is given in this format. That's why we are getting three cases like this. Now if we take another problem, it's not necessary that we get 1, 2, 3 cases like this. It might be just 2 cases, or it might be just 1 case. So because that our function is in this format, that is why we are having these 3 cases. Okay, now our primary objective, or now our objective is to find out which is the most suitable phi dash of x between these 3. Now you will be confused, like which phi dash of x you have to choose. For that, what you have to do is you have to substitute the value of x. That is, you have an initial root with yourself, right? What was that initial root? It is 0.5. So you have to substitute the value 0.5 in each of these phi dash of x, and then you will get a value. In the first case, you will get phi dash of x when you substitute 0.5 as 0.4038. Now again you had a condition that you will have to check the modulus of phi dash of x should be less than 1. So in this case, when you apply this condition, it is true. That is, again modulus, the value is less than 1, 0.4038. So in the second case also, when you substitute x is equal to 0.5 in this phi dash of x, you will get the value 0.4008, which is again less than 1. third case also you will get a value like 0.0272, which is also less than 1. So again you will be confused like which one to choose, but here you have a clear idea that see, among these three values, this is the least value that you have got, that is 0.0272. So keeping that in mind, what I'm going to do is I'm going to choose case 3, that is where I get least value of phi dash of x. When I substitute the initial root, I'm going to choose that phi of x. So here it is 0.0272, and then hence I am choosing this phi. So here I am going to choose the case 3 for my iteration formula. So as I said, we have considered the third case, and in the third case our phi of x is given by 1 by root of x plus 1. Okay, so since phi of x is equal to 1 by root of x plus 1, phi xn is equal to 1 by root of xn plus 1, and xn plus 1 is equal to phi of xn. That is the formula for iteration, and from that we will get xn plus 1 is equal to, since xn plus 1 is equal to phi of xn, xn plus 1 is equal to, what is phi of xn? That is, we have already written over there, that is 1 by root of xn plus 1. And hence we will consider this as the iterative formula, and we are going to start our iteration. So when we start our iteration, I am going to start it from 0. So when n is equal to 0, we get x1 is equal to, so when n is equal to 0, I get here x1, that is equal to 1 divided by, so this xn will change to x0, so 1 divided by x0 plus 1, which is equal to 1 divided by root of 0.5. Now you will be wondering how I got 0.5. 0.5 is nothing but your initial root, that is, this is x0. Okay, so you write here, substitute 0.5 plus 1, you will get an answer 0.8164. Next iteration, n is equal to 1. N is equal to 1, when I give n is equal to 1, I get x2, which is equal to 1 by root of x1 plus 1, which is equal to 1 divided by root of x1. I got the answer just before, and that is 0.8164. I am going to substitute over here plus 1, which I will get the final answer as 0.7419. Then I will give n the second iteration, when n is equal to 2, I get x3. x3 is equal to, the final answer will be 0.7576, and so on. So now we will have a look at the table so that you will understand the process more easily, like how the iterations are done, and then we will check how we will reach the final root.
Now let's have a look at the table. So here I have drawn 1, 2, 3 and 4 columns. So we have to do the iterations when till xn is equal to xn plus 1. So when we satisfy this condition, we can stop the iteration, and then we can conclude or come to a conclusion regarding our root. Okay, so the first column is nothing but the n represents the number of iteration that we have used in this particular problem. Xn is the approximate root. Now when n is equal to 0, x0, okay, in the place of xn you will get x0, and that is equal to 0.5, that we have already fixed this initial root, so there is no doubt in this. And in the next column, what we are going to do is, we are going to take the root of xn plus 1. Why should we take the root of xn plus 1? Because we have the formula xn plus 1 is equal to 1 by root of xn plus 1. So this denominator part, this part is what I'm going to solve in the third column. I'm going to find the answers for this denominator part. So when n is equal to 0, my x0 is 0.5, and the third column, root of xn plus 1, that is x0 plus 1, the root of x0 plus 1, or 0.5 plus 1, or the root of 1.5 is 1.2247. Okay, now you have to substitute this value in the denominator in the fourth column, and then you will get xn plus 1. Now xn plus 1 is nothing but x0 plus 1 in the first row, and that is x1, which is equal to 1 divided by this value 1.2247. So when I get 1 divided by root of 1.224, 1 divided by 1.2247, I get 0.8164. That is my what x1. Okay, then let's move on to the second row. Now in the second row, when n is equal to 1, xn is obviously it will be x1. Now the value of the x1, I will get it from the first row and the fourth column, and that is 0.8164. Then from that I can do the third column where I get the answer as 1.3477, and eventually I get x2. X2 is equal to 0.7419, because when I put the value x1 plus 1, it becomes x2, and I get 0.7419. So moving on, it takes around 6 iterations. When I land upon my fifth iteration, I get x6 as 0.7548. Okay, then x6 is 0.7548. I find the root 1.3246. The final column, I find out what x7 is. I get it as 0.7548, or sometimes you might get 0.7549. That's fine. Now I'm only taking into consideration this first 3 decimal places. Now this first 3 decimal places have like coincided, and from that I conclude that x6 or x6 here is what in a general form it is xn, and x7 with respect to x6, x7 is what xn plus 1. So my condition is satisfied over here. X6 and x7 up to 3 decimal places I have got it as an equal value, equal quantity. So there I stop my iteration and I come to a conclusion that this is the root, that is 0.7548 is the root for the function that you have that you were asked to solve.